Are we ready? All right. As stated, my name is Nathan Coulter. I use TCL to provide a variety of IT services to my clients, not particularly specialized. So what I do runs the gamut of the standard IT services that business entities need. Today I'm going to be talking about coroutines again. The people who were here last year may recall my presentation on what is called EuroTcl Coro Relay. And I think I'll start off with a question by show of hands. Who here has used coroutines to create, not just use coroutines, but to create or work to do some parsing activity?
What kind of activity?
Parsing. Parsing some sort of data formats. Okay. Okay, so very few. Okay, I thought a few more hands would grow up. Okay, I happen to do that quite a bit. For one reason or another, it has turned out to be a favorite pattern of mine. I will use coroutines to model the nodes, the conceptual nodes in a parsing structure. And that ends up being a sort of assembly line. The coroutines are communicating with each other as the nodes in the parse structure get created. So this is a follow-up to EuroTcl Coro Relay, which was a mechanism to allow coroutines to communicate among themselves. This is an event loop, and it's also based on coroutines. So why did I do it? To improve the performance of EuroTcl Coro Relay. I was using it in parsing. And so creating, the parsing trees can get kind of large, and the boundaries between, state transitions between the parsing nodes is kind of it's a nice natural place if you're trying to do things in a friendly way in a world of multiple processes. It's a nice natural place to maybe yield to the event loop and allow something else to happen, allow a user interface to get updated. So my parsers actually do that. When there's a state transition, they yield to the event loop. And that's the usefulness of the coroutines, is they can pick back up and perform this, what is conceptually a stack-based operation without growing the stack and without occupying the stack and without keeping the stack tied up. Today's library that I'm talking about, Coro Event, it's lower level. You can actually drop it into EuroTcl Coro Relay in place of the standard TCL event loop. It's created as a module, and there's a configuration option in EuroTcl Coro Relay to switch between this event loop, which is implemented entirely in pure TCL in terms of coroutines. What is this? It's essentially, I won't skip this. These are some notation that you'll see in the conversation today. $_ is just self, the current object. It's my own object system. To assign a variable, it's $_ $var1 value. And then when you see something like spawn, it's essentially a copy operation to create a new object. Okay, one more piece of background or a note. Yield to is actually analogous to a tail call. When you call tail call in TCL, you're replacing the current stack frame with the new routine. The same thing happens when you call yield to in a coroutine. The coroutine is the current frame. It gets replaced by whatever you yield to. So, in other words, the stack doesn't grow. Okay, we're just going to walk. This is actually the entire presentation on one slide. You can't read it, but that's okay. It's going to get broken up in a moment. We're just going to step through this simple process. It's a toy process, and this basically just illustrates that there are 4 steps to the process. There's a manager at the top, because there's always a manager at the top of things, and the manager is going to be proclaiming that he's managing, and in the meantime, he's going to be delegating work to the producer who produces things, who is going to, it's essentially an assembly line. The producer calls step 1, which then calls step 2, which then reports back to the manager what it's completed. So this is a simple process. This all takes place in this event loop. So as these different routines get called, they don't grow the stack. They're just happening essentially at one location on the current stack. All right, so the first thing that happens is we set up a procedure, an initial procedure to get things going. We spawn a scheduler. The scheduler there that's being spawned is actually an instance of this event loop. So that's what that is. And as you can see there, we can push things onto queues in the event loop. This is actually available. You can try it out if you're interested. There are multiple queues if you look through the documentation, which is integrated into the source code. You'll see that you can actually set up as many queues as you want in the system. So we push one item onto the queue, and then we just start the event loop by saying service. Now, when that line is hit, scheduler service, there's actually a yield to hiding down there in the implementation for service. So that's the point where this run frame, which is actually the operational frame, the active frame on the stack, is replaced by something else. And what it's replaced by is, well, the next thing that gets called, which is the manager. And now each one of these things is implemented in a coroutine. So we just have a sequence of coroutines that are stepping in to that point when it's their turn. So this is a loop. So the manager is just assigning things out in a loop. So you see an explicit yield to in this case, and that yield to is actually the TCL way of yielding from a coroutine, and then getting multiple arguments, multiple values back when it picks back up. A little long-winded, but that's the way to do it. Okay, so this coroutine yields, and then when it picks back up, it receives a count, which is the report of what's been done so far. In this toy example, nothing is done in this routine with that result, but of course the manager could produce some sort of report from that data. And so what eventually happens here is the manager pushes 10 things onto the queue, and then yields. So now there are 10 things sitting in this coroutine event loop. The manager yields, which means that what replaces the manager on the stack is the event loop itself. And this is one of the interesting characteristics of this system, which is the event loop is not ever present on the stack. The event loop is actually just another player, which is the default player that gets picked up when nothing else is happening. And the point of this presentation is basically we'll get to a slide where that illustrates how that happens. So this is the produce function. The manager yields and produce picks up. It's very simple. It does really nothing except once it is activated, it just calls step 1. It pushes something and then goes away. So it's really not doing anything. Step 1 performs just a extremely basic mathematical function with the input. Now the input here comes from this complex yield to statement, but that yield to represents the point where this step faded into the background, and that's the point where it picks back up. It gets an input, and then it does something with the input. which is essentially it passes it to the next step. Now that next step is put onto the stack or put into the queue, and then step 1 yields back to the event loop.
Just a quick question. Scheduler push itself does not yield internally, or does it yield too?
It actually doesn't.
It doesn't.
No.
So the control flow stays in this function until the next yield too.
Yes.
And nothing else.
Yeah. There's nothing else hidden here.
Okay.
The only time this function yields is right at that yield to.
Okay.
Step 2 is, these are all following the same pattern. Step 2 also yields there until it's called, and it gets some input, and then it does something else. Simple mathematical operation with the input, and then it reports back to the manager. So we have a loop here of operations, reports back to the manager by pushing something onto the stack and then fading into the background, at which point it's replaced. So what is taking the place on the stack in between these steps? Every time one of these steps yields, what actually happens, now we're looking at this implementation is probably about 400 or 500 lines in size. It's not huge. And we're just looking at kind of the core, the few lines around the yield to in the event loop itself. This is the coroutine that is replaced each time one of the other steps is finished. And how is it replaced? Well, it's calling each of those steps. It manages the queues. It takes something out of the queue. You don't see that here explicitly in the code, but you do see a tail call coroutine. Well, okay, you see an apply, which is embeds a tail call. So essentially that tail call right there is replacing the apply. That's not too informative for the purposes of this presentation, but that's actually what it looks like in the code, an apply and a tail call. But that $sign coroutine is a item of work that came off the stack. And so what's happening here is the event loop is taking something off the queue and executing it. And when it executes, the way it does that is it actually takes itself off the stack by yielding to that apply. So the event loop is replaced by a call to apply, which is then replaced by a call to the coroutine. And I think I left out, oh, okay. I got a little confused. That coroutine is the event loop itself. The item that was taken off the stack and executed is actually $sign script. So that's the item of work. So it's actually the event loop that calls itself back by, this is a bit of, I guess you wouldn't call it code generation, but the event loop yields to apply, which evaluates the work on the stack, which then tail calls the event loop. And that's the little bit that keeps the event loop running, even though it doesn't always exist on the stack. So it's not really running as an event loop all the time in the what we might in the traditional model of the event loop. For example, the standard TCL event loop, which is always occupying a place on the stack when it's active. Okay, so what about error handling? For the standard TCL event loop, we have background errors. Well, this is a point where this system differs a little bit. As you recall, this is the first example. This is the first slide where things get kicked off, the run procedure. And here we have an error which I just inserted that for illustration, that error will actually, flow control will never actually reach that line. But we can replace this procedure with a procedure that looks like this, where we're actually invoking the run procedure inside of a try. And this is pretty standard, capturing any error output. This try does take a spot on the stack for the duration of whatever is happening in the event loop, all work that is performed, which means that any error which arises in the course of any one of those steps will get caught and reported back here. So there's no need for background error functionality. Error handling is pretty straightforward in this case. Okay, that's actually the last slide. So I'll stop here for a moment and explain that my primary goal was to have an event loop which ran in pure TCL, which didn't hit select for I/O, for example, which can be slow. So it was really an attempt to improve performance. And I'm proud to report that this is slower than the standard event loop. So there's some work to be done still, but I think that can be reconciled. I think that's a small matter of programming. But that's it. That's the way this works. This is a little bit more specific than some of the other presentations, just to walk through some simple code. But that's what I'm doing with coroutines. And my question for one of the gurus, maybe Donald or anyone else interested in entertaining this question after this presentation is, this got me thinking about BGR and why we have the BGR facility. Why, for example, doesn't it raise errors back to V-weight, which does exist?
I could offer a possible explanation
Okay.
for this because originally the event loop started from TK, and in the case of TK you just don't have a V-weight, not always. For example, you just run the script, and at the end of the script, if there are windows here, it will internally start the event loop, and there is nothing here that will catch it.
But there is an interpreter at that point. But there isn't.
Yeah,
you're saying there's
exists,
nothing has been
the
called.
code is already done at this point.
In the original TK, there wasn't actually an interpreter to capture it.
Oh, well.
The event loop actually ran outside the interpreter. In fact, the main event loop actually is outside any particular.
Okay, that explains it. Yes, explains it pretty well. That's a perfectly decent explanation. Yes. So that's it. Are there any questions after this short presentation? Good, straightforward.
Do you have any example of any parsing activity done in this?
Yes. So I recently wrote something which turned out to be pretty much a full XML parser. I started out, my intention was to write something, reinvent Will Duquette's expand. Why do I reinvent things? I don't know. But that's what it was a code generation project I was working on. It ended up being pretty much a full, I realized that it was potentially a framework for any sort of parsing. And I turned it into that. And now I have both reinvention of Will Duquette's expand reinterpreted, and also a full XML parser, which you can find at YCL coro or YCL parse. It's called YCL parser graph, and that's actually a pretty complete example of this. You'll see all the coroutines, and you'll see that the nodes, as the nodes are created during the parsing of data, they're actually namespaces. So there's one namespace created, and there's an option to tell them to stick around. So when you're finished parsing the XML structure, you actually have a namespace for every node in the XML document that you can query, report, walk through, traverse, or you can tell it to make those ephemeral, make them go away as parsing proceeds. So I'm working on it. It's in pretty decent shape, but it's definitely a work in progress.